Welcome everyone to RNG Coalition's Wednesday webinar series. I'm Rachel Franco. I'm the Senior Manager of Leadership Advisory Boards and Member Services, and I'll be your host for today. If this is your first time joining us, or maybe it's been a little while since you've tuned in, Wednesday webinars are a space where we get together to discuss different developments, whether they be technological, policy, or education-based, anything really that's helping to drive forward the growth of renewable natural gas in North America and beyond. But today I'm very excited to be joined by the dream team from Bright Renewables to talk about biogenic CO₂, how renewable natural gas fits in, its use cases, and more. We would love to have your engagement, so I want to encourage you to submit any questions you have in the Q&A window at any time during today's presentation, and we will use some dedicated time at the end to speak to those. Contact information for today's presenters will also be available at the conclusion of the presentation. So without further ado, I'd love to introduce today's speakers, Alir Tahari, Graham Hartlett, and Perry Groves. Thanks so much for joining us today.
Thank you, Rachel, and thank you to everybody attending the presentation. I'm always happy to talk CO₂. Very appreciative that I got the opportunity here today. This presentation will be the first of three in our Recarbonize webinar series, talking about biogenic CO₂, the tech that'll make it happen, and how to rope it into your project. This first installment will focus mainly on a broad, high-level overview of the CO₂ industry, how biogenic CO₂ fits in, and where we can go using it on site. Quickly to cover the rough agenda for the presentation. First, it'll be what is biogenic CO₂, how RNG fits into the loop, capturing upgrade or tail gas, what a plant will look like, the various grades of product CO₂. We'll go through beverage grade quality and what that means, common use cases for the various grades of CO₂, rough rule of thumb project qualification, where CO₂ offtake is strong, why it's in demand, and high level boiling it down to a business case. Also, as mentioned, we'll have some open Q&A at the end. And if there's any questions that we don't get to or anybody would like to ask directly, our contact information will be there, so feel free to reach out. Firstly, I think important to delineate what is biogenic CO₂ and how it relates to the industry. On the left, you'll see a little graphic showing the carbon cycle, the biogenic carbon cycle. As a plant will absorb CO₂ from the atmosphere, it grows, eventually dies, decays, and through either combustion or decomposition will release that CO₂ back to the atmosphere, closing that loop, and that CO₂ will be available for other plants to do the same thing with. On the right, you see a fossil fuel fired power plant. And in this case, it's not a closed loop. The burning of fossil fuels pumps excess CO₂ into the atmosphere. And being that we're all in the renewable energy space, I think we're all pretty well aware of the implications that that has. Specifically focusing on now how RNG fits into that biogenic CO₂ loop. As we all know and love, the providers of the biomass, primarily backing our industry, consume plants and other biosources of energy for themselves. They give us the biomass to digest, and in typical fashion, through a variety of technologies, we can separate the CO₂ and methane. That CO₂ typically is vented back to atmosphere and the methane used for RNG. Where we can step in is on that vent to atmosphere end of the gaseous CO₂. The first step here in our generalized PFD, as shown here, would be a VOC filter. That's really the first step in providing some certainty around the outlet quality that we target. More on quality and grades to come in a bit. The second step shown here would be compression. We use an oilless head recip compressor, pretty standard for food and beverage grade CO₂ production. The third step is a molecular sieve to dry the gas. And to mention optionally, we can include some gas drying on the front end should it be a need, but particularly with three-stage upgrader tail gas, we only need this singular step here. And then steps 4 and 5 are really where the magic starts to happen. Step 4 is a condenser, and that orange loop on the right is a CO₂ based refrigeration system. We use CO₂ as a refrigerant as opposed to ammonia or freon to not only provide an environmentally friendly option, but with regulations consistently changing around freon, um, we have essentially a future-proof model here. And that CO₂ refrigeration system is completely divorced of the liquefaction. It's its own standalone piece, as is typical for this type of equipment. And as that gas charge that is now pressurized cools, droplets will form as the CO₂ condenses. And so the droplet will form from the outside in. This process can cause still gaseous contaminants to be trapped or entrained within the droplet. And so those droplets travel down the distillation column between steps 4 and 5 as they move towards step 5, the reboiler. That is a pool of already high purity liquid CO₂ that is dosed with heat to gas off. The gaseous CO₂ travels up the distillation unit, interacting with those droplets, disrupting them, and the gaseous CO₂ is now the carrier of the contaminants, resulting in high purity liquid droplets. I know it's kind of a lot, so happy to return to the slide or discuss in the Q&A to follow the presentation, but that's really the driving force behind the purification and liquefaction of the CO₂. And then lastly, on the right, you have your high pure liquid storage that is pretty typical for industry. You can have a variety of different storage systems, truck filling systems, or use on site. Kind of that scope is configurable for your end use or your offtake.
And Leo, we have one question already while we're on this slide,
Perfect.
which is entitled Capturing Upgraded Tail Gas. So the question is, what are the main integration challenges when you insert one of these CO₂ systems behind an upgrader?
Yeah, I think our tech expert on the call, Perry, would be well suited to jump in here.
Yeah, so the integration of the CO₂ liquefaction technology to that RNG upgrader is really dependent upon the RNG upgrader technology. Of course, we see different methods for RNG upgrading throughout our industry, whether that's amine upgrading, PSA, or membrane upgrading, and each of those have different conditions that the tail gas ends up with. And with that, there are some different integrations that have to happen. Just as a quick example, coming off of an amine biogas upgrader, the tail gas will typically have some water content included in there. And of course, as you see in the step 3 on the slide here, we typically need to remove water before going to the cryogenic processes in step 4 and 5. So if any additional water removal is needed, or maybe that water removal system needs to have a higher capacity. Different integration considerations like that are needed, but typically not a significant integration is needed, especially for an existing site, because this gas is already being vented. Fairly easy to install pipe from that vent directly feeding into this liquefaction system.
A second question quickly, Ilya. Or Perry, what is the CO₂ concentration of the exhaust gas coming out of the upgrader? And then just in general, what is the concentration of the various impurities that you see from an upgrader?
Yeah, good question. For the case of a bright upgrader, we'll see greater than 99% pure CO₂ as our tail gas stream. Other upgrader types, you could have 3, 5, 7, sometimes 10% methane slip going into that tail gas stream. So another good note to make here, as I discussed earlier on the steps 4 and 5, and that carrier gaseous CO₂, that CO₂ carrying those contaminants inclusive of methane, that doesn't have to just be vented to atmosphere. It's very typical that that would be recycled upstream into the upgrading process. And so virtually all of your methane slip would be recaptured in that loop, closing that. Otherwise, it'll kind of depend on the upgrading technology as well in terms of how much oxygen goes through with the CO₂, nitrogen, et cetera. So in our case, very small amounts, trace amounts, primarily being a 99+% pure CO₂ stream. Onto an example plant. This is a plant installation that we have in the Netherlands, not far from our global HQ, but a really good example of what a plant layout would look like, inclusive of upgrading. And just to further illustrate the point, this green box isolates what the actual liquefaction technology comprises of. Of course, the storage tank should be included in that, but as I discussed earlier, that part of the scope is configurable to the use case. Really, what you see here within the green box is all of the drivers for CO₂ liquefaction, and kind of in the back right is our containerized upgrader skid. So very modular design approach that we've taken, very, very efficient in footprint and relatively easy to accommodate by almost any existing upgrading site. Another site image here. This one's a better look into seeing exactly what the process flow looks like, relating that generalized PFD to an actual installation, just so you can get a better grip of what's going on. That first step, as I mentioned, the VOC filter, that's on the inlet side. That gets piped into the container for step 2, which would be the compressor. Of course, you can't see it now, but right beyond where the wall is, where the 2 is the location of that compressor. And then 3, the molecular sieve. And then you can kind of see it. It's a little bit difficult because it's black here, but you see the condenser and the distillation column. This would be your steps 4 and 5, along with the reboiler. And then exiting the system to the storage tanks are step 6, our storage. And we use 2 storage vessels here, and we have a truck filling station here that can select between which tank is getting emptied, etc. Onto the various grades of CO₂. There are
Yeah, sorry, just as these questions come
another
in, just
question.
to
Sure. Should I
quick
go back?
aside. Yeah. What is the flow capacity of the system in the photo with the numbers? I don't know if we have that on hand.
Ooh, Harry, do you know what the CO₂ side of Wabaco is?
I would definitely want to double check this, but this is on the smaller end of our standardized range of capacities. I believe this would be either a capacity of around 800 kilograms per hour of that CO₂ coming in, or 1,000 kilograms per hour of CO₂ coming in, somewhere within that magnitude. So about a ton of CO₂ coming in per hour.
And then the second question is, where is the CO₂ facility typically located relative to the RNG plant? Are they on the same location?
Yeah, so in typical fashion, they'll be installed next to one another as close as possible. And it's a little bit difficult to discern here, but off to the left of the screen, essentially, if you're standing in the spot and you turn to left at 90 degrees, you'd be looking at our upgrading system. So, 50 feet from one another, essentially as closely located as your site allows. And then you just pipe up your tail gas stream into the inlet of the step 1 VOC filter, and the rest is history. In terms of storage location, in this example, it's quite close as well as the previous example, but storage doesn't have to be right next to the equipment if the site design doesn't allow.
Thank you.
Okay, Returning to the grades of CO2, there are numerous grades of CO2. I'll touch on four here, four pertinent for this discussion, I would say. The first one being industrial grade. It's typically 99.5% pure. Some sources dictate that it's 99% pure, which coincidentally enough is in line with the tail gas of a three-stage upgrader. But due to the high market saturation and the low cost of production from other sectors, you have kind of a low value tied to this industrial grade CO2, though there is ample amount of offtake in the industry. So if you're negotiating a CO2 project, it could be a viable source of offtake for you, but probably not a high flyer on anybody's radar. The second one, food grade, 99.9% pure or better. Very strong value here as there's less market saturation and it's relatively easy to comply with. It's molecular quality at the end of the day, as is not the case with beverage grade, also 99.9% pure. Very high value, brings very good premiums in industry, but there are many procedural requirements, and I can touch on those at a high level on the next slide. But nonetheless, lab grade, 99.99+% pure. There's a high value here, but it's very difficult, aka costly to produce, and so it might not be the rabbit hole worth jumping down for the RNG industry. Here we have the beverage grade quality parameters. Outlined here are just the molecular requisites. Beyond this list, there's also some sensory requisites. It has to be odorless, tasteless, and clear, no appearance of color or turbidity in water. Otherwise, the molecular quality here would qualify for food grade as well. So it's really the kind of regulatory side of it that would be the barrier between food and beverage grade is offtake. If you see a CO2 system in market advertising beverage grade, it's almost always technically beverage grade molecular quality. There should be a clear delineation of that in terms of discussion. Beverage grade itself requires some other hurdles such as redundant storage system. Essentially, you need to have at minimum 2 vessels. That way, if one doesn't meet the quality spec, the other one can have offtake, and that CO2 can be non-contaminated, and the up to spec output product can go into the non-contaminated vessel. Otherwise, you have to do a fingerprint of the feedstock. There's some continuous and periodic analysis that has to be accounted for. So a significant amount of steps between food and beverage grade in terms of commercializing and bringing it to market. Although the ISBT Technical Committee for Beverage Gases is currently drafting guidelines and requirements for bringing biogenic CO2 and in broader terms, CO2 from alternative sources to market as a beverage product. So be on the lookout for some developments coming from that group over the next year. Here we have some common use cases for CO2, separated by grade. Industrial grade CO2 is typically used for greenhouses, and this would probably be the best application for this industry in terms of making a project feasible for the industrial grade CO2 as a product. Other uses could be welding gas, chemical manufacturing, concrete, use as a refrigerant. But as mentioned before, there's a high amount of saturation in the market, driving the premiums that you could have in terms of offtake down. Second, food grade, a great avenue for the RNG industry, specifically with some call them circular economies that you could have within, such as a meat processing plant, using CO2 on site for various processes. It might use the plant waste to make biogas and subsequent RNG, and then offset their purchasing of CO2 with some local production. And so food grade is quite an interesting model, but it's used typically in modified atmosphere packaging, freezing, controlled atmosphere storage, multiple food processing steps, and then refrigerated logistics and inerting as opposed to nitrogen inerting. Onto beverage grade, typically you'll see this as offtake to beverage bottlers to carbonate the product that they're selling. Otherwise, beverage dispensing systems and pressurized packaging also use CO2, but the main driver here for beverage grade offtake would be the actual carbonization of the beverage. And then lastly, as we touched on, lab grade, you use it as a calibration gas for GC, cell and tissue incubators, so kind of in line with the food grade controlled atmosphere storage and packaging. Similar thing, but requiring higher specification on purity, SFE, and CO2 lasers as well. So quite a few niche and interesting technologies there, but as touched on before, not always the most easily attainable purity.
So a couple of questions coming in, Ilya and Perry, and please keep them coming. CO2 is a big topic, and that's why we decided to do a series of 3 webinars. We'll talk about that a little bit later. We're going to get into some of the technical stuff in webinar number 2. But in terms of this one, a couple questions. Can you just discuss how dry ice fits into the picture in terms of a use case?
Yeah, so dry ice is most typically used in the food industry. Food processing, you could have refrigerated meat grinding using dry ice. There's also cold rooms that are dry ice refrigerated. Refrigerated logistics will commonly use dry ice, and so there is a good amount of synergy between our industry producing LCO2 and then converting that CO2 to dry ice. In terms of offtake, dry ice can be pretty regionally dependent. Same with liquid CO2, as we'll discuss in a couple of slides. But it's definitely a feasible path to follow, and there is some interest with some of the major dry ice brokers looking into biogenic CO2 as an alternative source.
And then a question for you, Perry. In some of the photos that we showed previously, did those CO2 systems produce industrial grade or food and beverage grade? And maybe you can talk to the standardization of the design for prior to LCO2 systems and what grade of CO2 we typically design for.
Yeah, and you beat me to the punch to discuss at least our technology and how we've standardized our outputs to food and beverage grade. So the sites that we've shown in pictures in previous slides, we're producing food and or beverage grade CO2. Of course, like Ilya has mentioned, beverage grade does have some specific procedural requirements for that. For example, redundant storage like we saw. So these plants would be producing, or at least the first picture we saw, because there's one storage tower, we can assume that's food grade. But as a standard practice for at least our technologies with Bright Renewables, we produce food and beverage grade CO2 as a standard, so that 99.9%. And as Ilya showed on the slide, I think previous to this or 2, some of those other contaminants that the ISBT specifies, we also comply with that as a standard.
Thank you.
Is that all the open questions, Graham?
They're coming in thick and fast, but we'll try and select them based on what slide you're on, and just keep everybody informed of the subsequent webinars we're planning on this topic. So much to discuss. So.
Deviating a little bit from the technical and the specifications, getting into rough rule of thumb project qualification. So how would a developer maybe identify a good project from a not so great one? First things first, I think most important to look at the production. 1 truck per day is kind of the benchmark, which is roughly 1 ton per hour. This eases the logistical end. Typically an off-taker would want a very regular, continuous supply of CO2. And so if you can produce at this volume, not only does it bring down your cost curve of dollar per CO2 ton of CO2 produced, which we'll get into in a couple of slides, but it eases negotiations on the logistical end. And so relatively important, I would say. Projects can pencil out and can make it work at flows lower than this, but it just does become a little bit more tricky to find that offtake and find the partner to manage logistics. In some cases, if a firm is managing logistics themselves, they could make it work, but for the intents and purposes of this call, I think 1 truck per day or 1 ton per hour is a good benchmark. The second one, inlet quality or your tail gas quality. Typically, we would say 90+% pure on the CO2 front with water removed. 95 is generally greatly preferred, as any distillation-based LCO2 system will have a recovery rate, essentially the efficiency of the liquefier to liquefy the incoming CO2. And as your CO2 concentration on the inlet side goes down, your efficiency goes down with it. 95+% on the tail gas really makes a good business case as your system is operating what we would call optimally. The third note, it might go without being said, but steady state operation is crucial. Again, these off-takers that you're working with in the private sector expect routine deliveries, and they're relying on these alternative sources of CO2 to stabilize their CO2 economy. And so if you don't have a reliable system, or if you're not operating in steady state, it can propose some problems in the development cycle. And then lastly, location. That is everything for CO2 value. And so remote areas and the coasts are the best value. And essentially, as we'll outline on the next slide, the closer you get to those coasts and remote areas, the better the offtake pricing for CO2 will be.
So maybe another question for you, Perry. A couple questions have come in about scale and size of plant and how to properly reference that. I don't know if you have a quick way to go from, let's say, 1,000 SCFM biogas going to the upgrader. What would we typically expect the size of the LCO2 system on the back end of that, just in rough terms?
I think that would be roughly a 1,500 kg an hour system, so right around 1.5 tons per hour. I know a 750 SCFM biogas flow will carry roughly that 1 ton per hour mark.
Okay,
So
so
anything north
a
of
good,
that would be good.
yeah, thanks.
Yeah, my typical rule of thumb for that conversion is your SCFM of biogas. If you can convert that to normal cubic meters per hour of biogas, that's roughly how many kilograms per hour you'll produce of CO2. So for example, the 2,500 SCFM of biogas converts, or excuse me, 1,500 SCFM of biogas converts roughly to 2,500 normal cubes. So you would typically expect around 2,000 or 2,500 kilograms per hour of CO2 produced from that.
All right, thank you.
So to illustrate the last point of the previous slide in terms of location, I drew up this map in Microsoft Paint. It's nothing pretty, but I think it gets the job done. Essentially, the further you are, or your site is from the central US, the higher the value of your CO2 will be. And this is because commercializing the CO2, in this case, in the biogenic CO2 case, will operate under a cost offset model. And so what a consumer would be willing to pay for a local producer would be in accordance with what they're paying from centralized production. And by the time it makes it to the East Coast or the West Coast, the value of that CO2 is baked into the cost from a centralized supplier, and that cost is primarily built with the logistical cost. And so that's why distance is the main factor. And the central US is kind of the epicenter for CO2 production. Remote areas like Alaska and Hawaii would carry significant premiums because not only do you have to truck to a port, you then have to transport on a boat and then truck to site from the port in Hawaii, Alaska, Puerto Rico, also inclusive there. So it can become a very attractive project, but projects in the areas in general are pretty scarce. So unfortunately, I don't think we're all going to be able to jump the gun and develop a project in Hawaii or Puerto Rico, and I'll take a nice vacation to visit site. But anything on the coast or approaching the coast is really where you'll find that high value offtake for your biogenic CO2.
There's a question about this map saying the map of strong CO2 offtake regions is interesting. What trends are driving demand in these areas?
Yeah, so you'll see different demands in different places. For instance, there's a lot of power to X going on in Texas. And so essentially using CO2 to possibly methanize hydrogen to create synthetic fuels, e-fuels such as e-methane, e-methanol. In the Southeast, there's some beverage processing as well as um, dry ice offtake for refrigerated logistics, things of that nature. There's a lot of fruit production here, and so the freezing of those products has to be done with CO2, or most economically done with CO2. When you travel north a little bit, you start to get into a lot of meat processing. And so we talked about a little bit earlier the CO2 demand for food processing, particularly meat processing. And then all along the coastal regions on the West Coast and the Northeast, there's a significant amount of beverage bottlers. And these bottlers, they could be spread all the way across the US, but the logistical cost of getting the CO2 to that consumer is what uh, drives the price up for those off takers. And then Wisconsin and Michigan, again, a lot of meat processing, dairy processing, et cetera.
And then a couple questions on applications and maybe just a high-level commentary on CO2 opportunities on landfill gas projects. Any thoughts there?
Yeah, there's a significant volume of CO2 on landfill for sure. The difficulty there is bringing that to beverage grade or making it acceptable in the food sector. I know there's some pushback against landfill gas in specific um, in use in those sectors, but given the volumes of the gas flows, there are some, maybe in the coasts, some industrial grade offtakes or particularly large industrial greenhouses would be a good one to hunt down if you were a landfill gas developer. In terms of technical adaptation of our system, as we kind of mentioned earlier, it would depend on the tail gas stream coming off of the landfill gas upgrader, which is a function of primarily how old the upgrader is, but also the technology deployed there.
Thank you.
Anything else while we're on this slide?
They're coming in, but I'll keep you informed.
Well, good, good. I appreciate the engagement. It's been fun answering the questions so far. Quickly, I think it would be remiss if we didn't touch on why CO2 is in demand. The US and other parts of the globe have been seeing a CO2 shortage over the past 5, 6+ years. And so it's crucially important to consumers that they stabilize their supply. And in essence, suppliers have been a little bit shaky, and consumers have had to pay exorbitant amounts to get their CO2 and keep production up, particularly in the beverage industry. And so that's been the catalyst to look towards alternative sources of CO2, seeing how we can stimulate the market and create hubs all across the country of local production, and of course, all in all, reducing the carbon footprint and all of the things that the RNG industry stands on. One thing to note here, in light of all of these CO2 shortages, historically there have been some pretty slow developments and some opposition for biogenic CO2 being that next frontier, the solution to the problem. But things are starting to open up. There's a lot more wind in the sails now. And so I think as we're hearing more and more about CO2 being a topic of discussion in RNG in general, I think that's kind of a titrated effect of the broad spectrum CO2 industry becoming more and more interested in the CO2 that we are currently venting. Okay, last slide of content, maybe a heavy hitter for some of you. This is a very, very rough, very, very high level, full of many, many assumptions business case. And I think this illustrates pretty well the value of CO2. This base case was that 750 SCFM of biogas, roughly 1 ton per hour system, basic of our 1,000 kg an hour system. And so what you end up having is a revenue model here, not really wanting to get into the CapEx of developing a biogas site and all of that, but just a revenue model to see what you can do with CO2 on a site. And so that dark blue line is your base case with just an upgrader. The data here that we've assumed is our upgrading case, so very high methane recovery, excuse me, recovery, very low methane in the tail gas stream. The light blue line is your LCO2 added on at an offtake price of $100 per ton, and the green line is the same, but at $200 per ton. And what I hope to illustrate here is that no, LCO2 is not going to blow the revenue of an upgrading project out of the water. But when you look at the project financials, specifically looking at your payback period, IRR, NPV, the project financials are quite good because if the site's already developed and the tail gas is already there, it's relatively inexpensive comparatively to develop just an LCO2 project on the back of an existing upgrader as opposed to developing an entire RNG plant. So here you've got, payback period at the $200 per ton model of 3 1/3 years. This is also not taking into account recirculating the recaptured methane slip. So in our case, you'd have a slight bump, but in some cases, maybe 5% methane slip in that tail gas stream, it starts to become increasingly valuable to recapture that and monetize the CO2. One thing I do want to note on this slide is the fourth item, this levelized cost of CO2, dollars per US ton. I alluded to it earlier. It's a really good frame of reference. And so I advise anybody that's qualifying a project to calculate that out and try to project what that would be, because it's a good indicator of how to approach the market, qualify the project. If your cost of production is, $300 per ton, either, something in the model is wrong or the project is just entirely infeasible. These systems have a non-linear cost curve when you talk about mass production. And so a 2,000 kilogram per hour system is not 4 times as expensive as a 500 kilogram per hour system. And due to that curve, you have varying levelized costs of production. And so this 1 ton per hour is a really good benchmark. You have a $62 cost of production, which when you approach the market for $100 a ton offtake, $200. In some cases, if you take on more scope, including verifying quality, managing logistics, XYZ, you can see offtake pricing go beyond that, though. As this serves as a high-level overview of biogenic CO2 and its application to industry, I don't want to steal too much from our third installment, the deep dive into the business case. So Very pertinent metric, I think, and when I do modeling for clients, that's the first thing that I try to calculate out just to make sure that the project can get greenlit, and then it gives you a good indication of what kind of offtake pricing you should be targeting when you approach the market.
Couple
I
of
think,
questions have
go
come
ahead.
through on it relating to the business case, but specifically, there's several questions on what happens with the non-condensable gases that are part of the process at the end, and linking to your reduction in methane slip. Maybe you can comment on that, either Perry or yourself, Ilya. How is that facilitated? What is the mechanism, and what happens to that gas?
Yeah. Essentially, that gas would exit the CO2 liquefaction system and be primarily comprised of CO2. Roughly 70 to 80% of that gas will be CO2, and it'll carry all of those non-condensable gases. That gas stream can be recycled typically to the digester or the preconditioning skid for your upgrader. Once there, we like to put it a little upstream with the compressor just because if you put it right at the compressor, we believe that it didn't give ample time for the gas to dilute into the biogas flow. And so the digester is really the best place. But the pretreatment skid is perfectly feasible, and it gives it time to dilute and go through the process as normal, closing that loop. And similar to a three-stage membrane, you kind of bring that back. You strip out the methane from the tail gas of the two-stage membrane and bring it back to the front for processing. We'd essentially be doing that with the non-condensable stream, eliminating that point of methane slip. And if you have a GC on site, you'll get a little bit, tiny, minute amount of methane loss due to sampling. Otherwise, the maximum of 50 ppm for food grade CO2 of methane you'll have in that. Otherwise, every molecule of methane would be accounted for and added back into the grid.
And thank you for that. And then a question about, do you provide the LCO2 and the upgrader together? Is that something that we can do as a overall project scope?
Yeah, in terms of project scope, we can do the upgrader package as turnkey, inclusive of pre-treatment, and then we can couple the LCO2 system with that. We can integrate the LCO2 system into other upgraders. We can also include CNG, LNG solutions on the RNG end, as well as some storage solutions, analysis equipment, truck filling, et cetera, on the CO2 end. So we bring quite a breadth of scope to these projects, and of course, they work best together, incorporated together, although our team has experience, for instance, adapting our LCO2 system onto a PSA. That's something that we've done in Europe. So we're happy to integrate kind of with anything that makes a technological case.
And then a technical question again. We talked about landfill gas and CO2 from that as a source and the obstacles associated with that. Any commentary on wastewater treatment plants and LCO2 from that source?
Yeah. CO2 on wastewater. Wastewater can have some atypical contaminants as compared to your standard dairy case. But we are configurable on the CO2 system to include various different types of pretreatment or gas treatment in general, whether that be low pressure filter vessels like we've seen to remove VOCs, H2S, even siloxane removal technologies we can integrate. And then depending on concentrations, we can sub out the low pressure design for high pressure vessels to remove those contaminants as well. So relatively configurable technology. Really the driving force would be by the time the CO2 gets to the condenser, we want it to be as clean as possible, as dry as possible. Otherwise, we're we're willing to package kind of whatever works to make that liquefaction step happen.
And a question for Perry. What is the typical recovery rate for your CO2 in your system?
Yeah, because it's a cryogenic distillation process, that is dependent upon the inlet quality of the CO2 coming in. Like Alir mentioned, for our situations, we typically will see streams of 90% or higher, ideally 95%. But coming from our upgrader, as we've discussed, since that's a relatively pure stream of CO2 at about 99% coming into our liquefaction system, we'll see recovery rates as high, if not higher than 95% for a stream in that example. So very high recovery rates. Of course, like Alir mentioned, if you take that non-condensable gas stream from this process and recycle it back to the digester or upstream process, you can also recover that methane and also that CO2 to reprocess and recapture as well.
And a question about the subsequent webinars that Ilya, you alluded to. What is webinar 2 and 3 about?
So I'm just going to move off the business case slide just in case we don't get the time, but I just wanted to reiterate a thanks to everybody, and again reinforce, feel free to reach out to any of us. We're always happy to chat. Sorry, Graham, what was the question? I just wanted to get that out
Yeah,
there.
there's you mentioned some other webinars that you're planning in the series, because the topic is quite big. There's lots of questions. And so just a reminder, what is webinar 2 and 3?
Yeah, so webinar 2 and 3 will be date TBD for the time being. Webinar 2 will focus on a deep dive into the tech, really getting granular with the nuts and bolts of our technology, as well as the technologies in industry that make CO2 liquefaction possible, and then talking about, in specific, what steps are needed to adapt it to a PSA, amine system, landfill. So kind of exploring those topics that we've touched on already in significantly greater depth. And then webinar 3, as I had a very high level business case here, webinar 3 will focus on what it actually looks like, discussing more of the steps towards commercializing the product and trying to inform whoever's interested on what the semantics look like in bringing this product to market and building it into their portfolio.
Now, the technical question for you, gents. Are the ISBT constituents continuously measured?
So there would be at the offtake from the storage system, there's a measurement essentially certifying each truckload for a list of 40 or so, I think a touch over 40 constituents possible. Though that list is part of the regulations that the Technical Gases Committee is working on. So it might grow, but that's the most continuous measurement as I understand. Otherwise, lab testing and things like that would have to be done on a periodic basis.
Great. Okay. Well, thank you, Ilya. I think we'll hand it back over to Rachel to conclude.
Absolutely. Thank you, guys. And thank you to our participants today for sending in so many great questions. As Graham mentioned, this is a broad topic. We're looking forward to getting these gentlemen back on our schedule for webinars 2 and 3, so stay tuned for that. Check back on our website a little bit later today. There will be a recording of this that you'll be able to watch later, share with your colleagues. And just as a reminder, we do have a webinar scheduled next week, same time on August 20th with Morrow Energy. So thanks again to the gentleman from Host. We appreciate your time and the work that went into this. And we look forward to seeing you all again very soon.
Yeah, thank you, Rachel. It's been a pleasure.
Thank you. Bye-bye.